to today's webinar of optimization of quality, mold, and part. My name is Ralph Picklow, Vice President of Sales with Cimatron Technologies. We also have John Barnes, the application engineer, and we also have Ken Chang from Moldex, an application engineer. Today's webinar, we're going to go over several things. We have an agenda that we'll pull up in a minute here, but first, you will be able to submit some questions. There's a question box on the right-hand control panel. Just simply type in your question, and we will, at the end of the presentation, we will read the questions and answer the questions. We'll try and get through all the questions. If we do not, we will follow up via email with the questions and answers. First of all, a little bit about Cimatron. We're a worldwide leader in CAD/CAM solutions for design and manufacturing of tooling. 25 plus years of experience, operations in 35 countries, over 40,000 installations worldwide. Cimatron's customer delivers tools faster than the industry best in class. About Moldex. Moldex is the world's largest plastic injection molding CAE. 80% experienced engineering professionals. They have 9 global offices, 100 plus international resellers, and they have strategic alliances with several high-end softwares. Today's agenda, the topics that will be discussed in this session, we'll look at the injection molding CAE. We'll look at part and mold design optimization. We'll also cover introduction of Moldex 3D, e-design, and we'll go over the Moldex analysis and the results. I'm going to turn it over to John Barnes, and we'll continue on.
Okay, thanks, Ralph. Moldex has a rich history of innovation and growth as a true industry leader. After combining various resources from academics, industry specialists, and customers, the predecessor of Moldex 3D was first released in the early 90s. It is believed to be the world's first CAE program to run on a Windows platform. In 2004, Moldex 3D was the first injection molding CAE to support parallel computing. Here is a small sampling of global customers whose names you might recognize from diverse industries. You can see there's Yamaha, Delphi, Foxconn, Unilever, some pretty big names here. Moldex 3D has 3 products that cover a wide range of CAE needs. Starting with Explorer, we provide product designers with CAD-embedded tools for exploring various design concepts. When designing molds, eDesign offers mold designers easy-to-use interface with accurate computations to verify complex runners, gating systems, and cooling channels, as well as predicting warp and other defects during the molding process. Moldex 3D Solid Shell offers more advanced tools to decrease your product-to-market time and to improve the quality of the design with comprehensive analysis results. Today's focus will be on the mainstream product, eDesign. These 3 products present a single unified platform for all designers and CAE specialists at every stage of the product development cycle. It integrates all of your innovation, efficiency, and productivity to reach your design expectation and product optimization. In the design phase, there are several often difficult key decisions which product designers must make. For example, how to design the proper wall thickness and how to deal with thin wall products. What potential defects will be found during the tool design and molding process? These questions are extremely complicated and frustrating for product designers. What's worse is that they often do not have any tools to prove out their design concepts. Many times, the only way out for them is to hold the tool builder responsible for these corrections. My background is tooling, and I happen to know the tooling guys are so nice, they often do this for free anyhow, right? The truth is, these problems should have been solved before the mold design phase. The reality is, both of them definitely need to think about these issues. The primary tasks of an injection mold include the accommodation and distribution of the melt, precise temperature control to properly solidify the material, and ejection of the molded part. Additionally, a mold has to provide good tooling or steel conditions and mechanical functions such as slides and lifters, all while holding tight tolerances on the part after the warpage and shrinkage of the solidification of the material. This places an enormous challenge on the mold designer. E-Design supplies the tools to help evaluate the size and layout of the runner system, gate location and type, adequate cooling circuit, and appropriate number of cavities. Taking some of the guesswork out of the design process is made further efficient since E-Design can take CAD data directly from your 3D mold design in order to simulate the actual process conditions before any steel is ever cut. As you will see later in this presentation, with parallel computing ability and the few required steps to get to the simulation, you will see that there is very little time invested for maximum return of prediction and knowledge. In addition to the challenges that I just mentioned, under the best of conditions even, injection molding is still a complex technology that also introduces these challenges. If not handled properly, there may exist various flaws either by defects in the mold or improper mold process settings. And here we see examples of a short shot. Of course, a short shot is a molded part that's not completely filled. Burn marks, black or brown burnt areas on the part, usually located at the furthest point from the gate where the air is trapped. A weld line, also known as a knit line, where the flow front meets. Sink marks, which would be localized depressions, usually in the thicker areas of the part. Warpage, which of course is just the part that's been distorted during the shrinking process. And flash, which would be excessive material, usually in thin layers that leak out at the parting line and of course exceed the normal part geometry. With the CAE approach, a process simulation is launched before the prototype mold is ever constructed. In other words, prototyping is done on the computer. In the design phase, a part designer evaluates the influence of material selection and processing on the various part specifications. The analysis is based on physics principles and actual conditions, rather than a rough estimate from handbooks. Part wall thickness can be optimized to facilitate its processing feasibility and product performance. Part design is very flexible since the real mold has not been built yet. In the mold design phase, the design is further refined by adding molding considerations. Runner system and gate are designed according to the process dynamics simulation. Cooling system is optimized to shorten the cycle time and improve part quality. The molding trial on the computer is possible before the actual molding trial is ever conducted. In this way, mold construction has not begun until the molding trials on the computer meet the requirements. The interrelation of part design, material selection, part performance, and processing is all taken into account. Modification of part design and mold design is flexible and concurrent. After the mold design is accomplished, the mold is constructed and actual molding trials are conducted to evaluate the mold's feasibility. The time and materials, also known as money, used in molding trials and part testing are minimized since the design has been comprehensively evaluated. Production can then begin and the product development is finished. From concept generation through CAD design, tooling, and production, the collective intelligence of your key personnel is enhanced by the seamless communication supported by Moldex 3D eDesign. The flexible licensing, user-friendly workflow, and approachable interface all make eDesign a highly efficient platform for cross-department collaboration and confident decision-making. As we have stated, injection molding is complex. It involves many design and process variables. Cost-intensive and time-consuming trial and error procedures are too often accepted as the normal process to evaluate the related parameters. In recent years, new challenges in the injection molding industry have risen. Delivery time and time to market are getting shorter. The product development time as well as tool delivery time has been shortened in the face of global competition. In fact, unprecedented global competition is pressing industries to meet various customer demands for better quality, lower cost, eco-friendliness, and so on. People keep looking for more cost-effective and smarter ways to improve the efficiency and profitability. Finding problems and learning solutions from trial and error is a traditional approach and very cost-consuming. To effectively eliminate uncertainty and financial losses associated, an efficient engineering tool becomes more and more necessary to increase competitiveness. By simulating the filling process of injection molded parts, Moldex 3D ensures both originality and manufacturability in the design and molding phase. Design teams can easily use Moldex 3D as a collaborative tool to identify potential problems and solutions. Although Moldex 3D is incredibly powerful and accurate, it is surprising how easy it is to use. There is no mesh preparation. The part model is simply imported as an STL, and the mesh is generated automatically. The runner and gates can be drawn in eDesign or imported either as STL or wireframe, which would permit parametric attributes to be assigned inside eDesign, which means that the runner, gates, and water circuit diameters can all be modified without the need for data exchange. eDesign provides the most friendly pre-process environment. The most advanced meshing technology is employed to help users generate true 3D solid mesh of outstanding quality without the need for any pre-process work. eDesign Runner Wizard provides powerful yet intelligent guidance for your design. Now you can define runner systems and optimize the mold design with ease. eDesign also offers a cooling channel wizard. Users can quickly define the cooling circuit and configure it inside eDesign as an alternative to importing it from another CAD system. More advanced options are also available to enable customization according to the user's requirements to automate the creation of an entire cooling system and subsequently speed up the optimization. Next, let's have a closer look at the Moldex 3D modules. Moldex 3D standard modules are flow, pack, tool, and warp. Advanced modules are fiber, multi-component molding, hereafter referred to as MCM, reactive injection molding, optics, viscoelasticity, and injection compression molding. eDesign Flow gives you accurate insight into solid plastic flow behaviors from a macro view to a micro view, such as fountain flow, inertia effect, and gravity effect. Users can better understand how the solid melt flow progresses, accurately identify where the knit lines are, and examine short shot problems. If more than one gate is used to fill a part, you will see in different colors the material contribution from each gate and where they meet. The type of animation that you see on the screen now is easily captured within Moldex 3D. This is actually just a GIF file, and it can be pasted into the body of an email and sent to your customer. eDesign Pack incorporates material compressibility, or PVT, change to account for the density variation and melt flow behaviors in packing process for thermoplastic materials. Its true 3D technology can help you precisely determine gate freeze time, efficient packing time, and proper packing pressure to minimize areas of high volumetric shrinkage. Here we can see the packing volumetric shrinkage. eDesign Cool, with its true 3D analytical core, can accurately analyze the mold temperature, the efficiency of cooling channel layout, and the required cooling time in the design phase. It is a useful tool to detect potential defects in the mold cooling system, such as unbalanced cooling, hot spots, and prolonged cooling time due to poor cooling efficiency. You can accurately evaluate the cooling efficiency to further optimize the cooling system and reduce cycle time. Here we see dynamic slicing through the part in order to look for hot spots in the part. This will help us fully evaluate the cooling system. eDesign Warp provides users a true 3D simulation tool to anatomize the causes of shrinkage and warpage and further control these defects before the mold is built. You can easily and efficiently improve the part quality and optimize design. For fiber-filled material, eDesign Warp incorporates fiber composite theories and the fiber orientation results from eDesign Fiber to predict its anisotropic shrinkage and warpage. Here we can see a scaled-up animation of the warpage behavior. I can't help but think of a specific automotive headliner part that I worked on just a few years back that could have really benefited from this kind of prediction. We knew it was going to warp, and we tried to cut the steel safe, but as I recall, I think that we recut that mold at least 4 times before we finally produced a part within spec. Moldex 3D Fiber accurately simulates the 3D fiber orientation in mold filling process and further calculates the process-induced anisotropic thermomechanical properties of fiber-reinforced plastic parts. Users can understand the 3D orientation of fiber and further control the anisotropic shrinkage of fiber-reinforced parts. Here again, we see dynamic sectioning of the part in order to better understand the fiber orientation. Here we can see the type of influence that fiber has when producing this part. Moldex 3D viscoelasticity can predict the residual stress points, which can be a weak point on the part. You can see from comparing the left to the right how accurate the prediction is. eDesign multi-component molding gives you a powerful tool to accurately analyze the interaction of different components and further optimize product design. Users can freely model any kind of metal or plastic inserts and perform comprehensive analysis. With eDesign MCM, you can predict the prolonged cooling time, asymmetric shrinkage, and two-color or overmolding processes. and consider warpage of the different material combinations. Here is an example of the MCM where it's looking at steel inserts around the plastic and checking them for deformation. Here's another animation that shows the warpage behavior during the overmolding process. Mold-X 3D is the only CAE solution which supports parallel computing for flow, pack, tool, warp, fiber, MCM, and so on. By utilizing the strength of multi-core computers, the time required for analysis is greatly shortened. Mold-X 3D parallel computing technology supports PC clusters as well. Here we can see another demonstration of the software's accurate prediction of what looks like a venting issue. Here we can see progressive short shots and accurate prediction of the filling pattern. Mold-X 3D not only simulates the part in true 3D, but also the runner system. You might question why this is important. The reason is because of what is called shear heating phenomenon. While the material is flowing through the runner system, friction is creating heat. This heat does have an impact on material flow, and the next few slides will demonstrate this. The picture on the left is the left half of an actual shot of an 8-cavity mold. The simulation picture on the right predicted it due to temperature influence from the runner. And you can see where it says cold and hot, that temperature difference causes the inner cavities to fill faster. So the conclusion here is that the runner should also be analyzed in 3D to derive an accurate and realistic result. Let's take a look at another similar example. Logic would tell me that gate C would fill ahead of A and B since it is along the straight path of the filling material. But in reality, it lags behind A and B. And here we can see why. Note the heat pattern as illustrated by the darker orange color. We can see that the A and B are hotter than C. Here again we see the accurate prediction of flow pattern when compared to the real molded parts. This could only be achieved by calculating the shear stress in the runner system. These are the kinds of variables that are often not considered in traditional mold designs and cannot be predicted accurately without 3D CAE software. An extensive material database comes standard with Mold-X 3D. Any materials that are not in the database can be added easily. Best-in-class technical support can be accessed globally. Yeah, and the North American office is in Novi, Michigan. Okay, next let's take a look at some examples. The first thing that I want to show is what I started with in Cimatron. I have a 3D mold design here, and let me turn a few things off and on real quick. All right, so I've got a 3D design ready But what I'm actually going to take into Moldex is this. I'm taking a bounding box that represents the A plate and the B plate. I'm taking the cooling circuit, of course the part, and the runner system. But in this case, I only took the wire frame. I didn't take, the only thing that I took as an STL was the part, and everything else was wireframe in order to set the parametric attributes inside eDesign. Let's take a look at that. Okay, so here in eDesign, we have the part that I brought in as an STL, and of course the wireframe. So I'm going to pick on the cooling circuits first, and we're going to assign an attribute as a cooling channel, 0.438 in diameter. And next, let's take the runner. And we're going to assign the attribute of cold runner, and this diameter will be 250. And this one also is a cold runner. The diameter is 0.188. This one as well. And lastly will be the gate. Okay. And now we're going to just go through, excuse me, some of these steps. Yeah, I forgot the melt entrance. And the mold base. The mold base, again, is just a size representation of the A and the B plate. You're going to need the attribute for the cavity as well. Okay, now we're going to generate the mesh. And you can see that I have an accuracy level of 1 to 5, 1 being the fastest, 5 being the most accurate. And I'm just going to hit OK here. And then choose Generate. And while that is generating, I'd like to go back to the PowerPoint for a second. And I've got a couple of customer stories that I want to quickly share. The first customer story is for Unilever. Unilever is one of Moldex 3D's loyal customers. We are very pleased with the return on investment of Moldex 3D CAE plastic injection simulation. Here we see a famous cologne product of Unilever. They took its cover into Moldex 3D simulation. For this part, the main problem is heat accumulation near the bottom. In order to cool down this area, additional time would be required at the cooling stage, increasing the cycle time. Moldex 3D provides excellent prediction for the high temperature area and the suggestion to enhance the cooling circuit design above the top of the part. After the simulation, the problem has been solved successfully and the cycle time will be reduced by 1 second. Yes, that's just 1 second. But that 1 second saved €2 million for Unilever. Moldex 3D and its users play an important and irreplaceable role at Unilever. Next, we have Lego. Of course, Lego is a famous toy maker around the world. They have been using Moldex since 2001 to improve their product quality and optimize their product and tooling design. Moldex 3D flow simulation is the standard procedure for 90% of their products. Their CAE analysts will examine the simulation result and make educated decisions to enhance quality control and cycle time. Yeah, and we can see in the picture here we've got 1, 2, 3, 4, 5, 6, 12 cavity part that has a pretty crazy runner, and it's very important that that all gets balanced out. And as you saw in the previous slide, what looks to be balanced may not actually be balanced based on the heat the runner is producing. Okay, next we have Samsung. The Samsung Group, of course, is a multinational conglomerate corporation headquartered in South Korea with an annual revenue of over $150 billion per year. They're a dedicated player in the electronic consumer goods. Samsung Digital Division used Moldex 3D to predict plastic warpage and also evaluate the efficiency of cooling systems. For this skeleton of a digital camera, they enhanced the cooling design following a Moldex 3D suggestion and successfully reduced cycle time and material cost. Moldex 3D solutions benefit Samsung not only digital components, but also in their consumer parts. They have used Moldex 3D since 2003. Since then, more than 10,000 parts have gone through Moldex 3D analysis before going into production. Next, we have Cellcomp. Cellcomp is a market leader that develops and manufactures chargers for major mobile phone manufacturers. Power adapters based on Cellcomp's own product platform are also used for cordless phones, Bluetooth headsets, media players, modems, and routers, point-of-sale devices, as well as notebooks. They utilize Moldex 3D simulations on their prototype designs, even though 80% of their products contain metal inserts. As you can see here, Moldex has been able to save Cellcomp a lot of money through reduced warpage, wasted runner material, and improved cycle times. Okay, so we're going back into the eDesign, and we're going to look at the mesh that was created automatically, and I'm going to dynamically clip across the mesh and show you what it looks like. Here you can see the 3D filling inside of the mesh as we clip it away. Yeah, and of course, the runner is also done in 3D. So there's really nothing more to do with this one other than save it and take it into the project. And that's what I'm going to do now is I'm going to open the project. Now, we actually did do 2 different runs with this part. I want to show a few things on run number 1, and then we'll talk about what we changed, and then I'll show you run number 2. So first, let me go to run number 1. I'm going to click on filling, and we're going to view the filling pattern in this model. And what we're going to be looking for is temperature problems and warpage in this run. Okay, so let's have a look at the filling pattern. Next, we'll look at the melt front animation. And this will show us the air traps. Next, we're going to look at warpage. And here you can see what we're looking at right now is the X displacement, X being the longer axis here. And you can see that on the chart, we're talking about 1.6 millimeters. So, I mean, this part is not being adequately cooled, and therefore there's much more deformation than we would like to see. We can animate this one as well to exaggerate what that looks like. You can see how the part will shrink and warp. Okay, now let's have a look at the cooling lines on this one. And you can see that we don't have any cooling in the center of the part. In fact, we'll have a look at the temperature range real quick before we go in to show the second run. Now, what we really want to look for on this part is a difference in heat from the inside of the part to the outside of the part. And you'll notice that the back side of the part is, blue and green, ranging from 90 to 100. and the top of the part is more yellow, which is like 120. So it's a pretty big difference, and potentially a problem. Well, evidently it's a problem because we're seeing it in the warping stage. So now let's have a look at run 2, and we'll show what we did to improve it. Here in run 2, you can see that we added another line in the baffle to try to bring more cooling closer to the part. So let's have a look at the cooling and see what the difference is with this one. All right, now as we interrogate the temperature, we'll see that there's not as much variation from the bottom of the part to the top of the part, and of course it's being better cooled by the baffle. And now if we consider what the warpage is like as a result, we'll compare the two. And here we can see that at the worst case, we're at 0.25. So we went from 1.5 mil to 1/4 mil in warpage result. So it's a dramatic difference. All right, now we'll go back to the PowerPoint for a second here. In closing, the concept is simply that if both product and tooling designs are verified early enough in the design stage, it will help to eliminate unknown issues and optimize the entire injection molding process, which leads to higher margins and shorter delivery times. This can become a real competitive advantage over those who decide to stay with the traditional trial and error approach. For tool makers, there is also the added benefit of being able to provide such a service. For a long time, CAE software was too cost prohibitive for tool shops. Now, however, it is much more affordable and will likely become commonplace in the not too distant future. Cimatron understands this and wants its customers to be on the leading edge of technology, which is why we wanted to bring these ideas to your attention. Thank you for your time this afternoon, and we appreciate all of you attending. And of course, we'll have a question and answer session.
Thanks, John. Again, you can simply type in your questions in the right-hand side in the question box. We do have one question. How many users are out there? Again, one is for Cimatron, there's 40,000 plus. For Moldex, there's over 5,000 worldwide. Another question we got is, what's the difference between Moldex and Mold Flow? Ken, would you like to respond to that?
Yes. As you could see during the presentation, we could generate a solid mesh, not only cavity. We are able to generate the runner with a 3D mesh. And using our solvers, we could capture the shear heating phenomena in order to get a good warpage result. This is a very big feature. And meanwhile, we also support parallel computing. So as long as the users could provide us a good hardware, then simulation time won't be a problem to simulate 3D mesh.
Okay, thanks, Ken.
Thank you.
I don't see any other questions coming through.
Here comes one.
Here's another one. Will it run on Windows XP?
Yes, we support Windows XP and the Linux as well.
Okay. Okay, I think that's it for the questions for now. This webinar is being recorded and can be viewed later at a later time. We will be sending out email notices for all that have attended and signed up, and you'll be notified when you can view the presentation. Again, thank you for your time this afternoon. We really appreciate you taking some time out. And feel free to contact us if you have any questions about any of the products. Thank you again.